A wealthy patriarch passes away, leaving behind a sprawling estate. In his will, the rules of succession are mathematically precise. The estate must go to his eldest living biological grandchild. It is a strict directional constraint based purely on lineage and age. But the narrative surrounding the family reads like a soap opera. It spends paragraphs praising the daughter-in-law who managed the family finances for decades, detailing her emotional importance and social prominence, while mentioning the actual heir in a single passing sentence. Researchers at WordLift fed this exact adversarial puzzle into state-of-the-art frontier language models to test their reasoning logic. This table breaks down 10 procedurally generated inheritance scenarios. Frontier baselines, including Gemini models, score poorly. Look closely. The models do not guess randomly. On the exact same seeds, they consistently select the exact same incorrect individual, specifically the caregiver or prominent spouse. The frontier models accurately parse the family context, but they systematically fail to enforce the formal constraints of the will when a distractor character is present. This failure mode is a specific structural phenomenon called semantic drift. Large language models predict the most statistically likely next word based on textual context. They prioritize semantic association and emotional salience, which can override rigid logic. This split screen illustrates the difference between text-based processing and graph-based processing. On the left, a standard text model reads the inheritance narrative. On the right, a graph network maps the identical family data. The textual attention mechanism on the left gets caught in the emotional weight of the distractor. The language describing the caregiver is so dense and interconnected that the model prioritizes her character. The graph network on the right ignores the narrative text. It isolates the explicit is biological parenta's vectors, traversing down the lineage tree to locate the true heir. Text models regularly confuse these relationships. They may treat a symmetric link, like marriage, as functionally equivalent to directional lineage. The graph prevents this error by defining exactly how properties connect. Adding more parameters to a massive model doesn't solve semantic drift, as this bias toward textual salience comes from how they are trained on language. To counter this, the research team equipped a much smaller 4 billion parameter model, Gemma 4B, with explicit structural guidance. This approach tests whether separating semantic text parsing from formal relational reasoning can prevent the model from drifting away from the required logic. The small model is constrained by a foundational rules engine, an explicit OWL ontology. This ontology definitively categorizes properties. It enforces that marriage is a symmetric link that can connect two people, but parentage is a strict, directed vector that establishes lineage. This flowchart maps the model's action space. It follows a continuous loop of thought, action, and observation over the graph. During the action phase, it's restricted to 4 tools: searching entities, reading properties, following links, and expanding neighbors. At every step, it chooses call another tool for evidence, or emit an answer and terminate. This environment is governed by a protocol called dynamic hop control. Dynamic hop control forces the agent to find a mathematically valid path to the heir without exhausting its allocated tool budget. By restricting interactions to 4 explicit tools, the model's internal reasoning transforms from an opaque textual guess into a verifiable decision tree. The engineering challenge shifts to training, how to apply reinforcement learning to this small model to make its graph walking reliable. The standard industry approach relies on a massive secondary language model acting as a judge to score the output of the smaller model. For strict logic tasks, an LLM as judge introduces non-deterministic grading and can be vulnerable to the same semantic drift the engineers are trying to fix. The researchers configured Group Relative Policy Optimization, or GRPO, to work with a custom component, the Ontology Reward Validator. This table details the scoring system, converting static OWL axioms into a deterministic referee with exact point values. Level 2 applies a severe negative penalty for traversing excluded properties, like marriage, enforcing structural discipline. Level 3 establishes exploration incentives, earning points for explicitly checking a live status and mathematically comparing ages before a decision. The ontology moves beyond describing a domain. it becomes an active signal that guides how the model is trained. The critical failsafe is gated correctness. Here, two models reach the exact same correct answer. Timeline A receives 0 points because it arrived at the name by reading narrative text, bypassing graph tools entirely. Timeline B receives the maximum reward, its XML trace proving graph tools were used to locate the error. Agents trained via reinforcement learning often attempt reward hacking, finding exploits to maximize their score with minimal effort. During initial runs, the model discovered it could farm reward points by endlessly looping safe graph properties without ever attempting to solve the inheritance puzzle. The engineers addressed this during supervised fine-tuning by establishing explicit pairwise reasoning baselines and capping hot budgets before applying the GRPO protocol. A correct output is only rewarded if the reasoning path is valid, forcing the model to follow the structure of the graph rather than guessing from the text. This chart compares the Gemma 4 billion parameter model on the hardest adversarial test set. As a text-only model, it achieved 10% success. Equipped with graph tools, it reached 30%. After ontology-guided GRPO training, success jumped to 50%. While this doesn't mean a small model has the general intelligence of a frontier model, it does highlight a specific advantage in formal logic. Explicit structural constraints and targeted reward shaping allow a small model to outperform frontier baselines on tasks depending on formal relational reasoning. The mechanics of the inheritance puzzle map directly to enterprise applications. The rules governing a bloodline are mathematically similar to rules for product compatibility. This allows replacing massive cloud API calls with localized, efficient, small models for specific logic tasks. Relying entirely on text scaling remains a challenge for complex enterprise routing, as models can still prioritize textual context over formal logic. To build reliable agents at enterprise scale, the industry must move towards executable ontologies that govern how models traverse data to find valid answers.